All right, let's jump right in. Today we're talking about a massive breakthrough where AI is tackling one of the biggest roadblocks in quantum computing. We're going to see how it's helping us build quantum machines that are not just powerful in theory, but actually practical. This is really cool stuff.
It's not science fiction anymore. Quantum computers are real. We've built them. And their promise is just staggering. They could solve problems that our best supercomputers today wouldn't crack in a million years. Think designing brand new medicines or creating unhackable networks. The potential is just huge. But, and this is the big but, here's the paradox. For all that incredible power, today's quantum computers are unbelievably fragile. They make mistakes, a lot of them. So you have this unbelievably powerful machine that struggles to give you the right answer. That's the one single problem holding back the entire quantum revolution. So how on earth do we fix that?
To really get the solution, you first have to understand the problem. And it all boils down to what we'll call the quantum conundrum. It's about the very nature of the machines we're building today.
See, we're in what scientists call the NISQ era. That stands for Noisy Intermediate Scale Quantum. And that one word, noisy, is everything. On the one hand, you've got this incredible, world-changing promise. But on the other, you have the messy reality. Quantum states are so delicate, the slightest vibration, a tiny temperature change, can make the whole calculation just fall apart. It's called decoherence. And it means our perfect textbook quantum algorithms often fail spectacularly when you try to run them on real hardware.
So, if our standard human-designed methods are hitting a wall, what's the plan B? Well, it turns out the answer might not come from a human at all, but from a brilliant, nature-inspired AI.
The technique is called grammatical evolution, or GE. Now, forget everything you think about coding. This isn't about a person writing lines of code. Think of it more like digital Darwinism. It's an AI that evolves programs. It starts with some basic building blocks and a set of rules. It's grammar, and it literally learns, through trial and error, how to build the absolute best, most efficient quantum circuit for one very specific job. So how does this evolution actually work? It's a surprisingly simple but incredibly powerful loop. First, the AI just spits out a whole bunch of random quantum circuits. Total chaos. Then it tests every single one in a simulation to see which ones are even remotely good. It takes the best performers, the fittest, and uses their good bits to create a new generation of circuits. Then it does it again, and again, and again, for thousands of generations, constantly refining until these circuits evolve into something remarkably elegant and effective.
Okay, a cool idea is one thing, but you've got to prove it works. So, researchers set up the ultimate test, a head-to-head competition between this new AI method and the old-school gold standard. And they did it on a real, live IBM quantum computer.
And here are the fighters. In one corner, you have the standard textbook version of Grover's search algorithm. Think of it as a generic, one-size-fits-all Swiss Army knife. It's designed to work for any search problem. In the other corner, you had the AI's creation, the evolved circuit. This thing is a custom-forged scalpel, designed by the AI for one and only one purpose. So the big question is, on a noisy, real-world machine, what works better, the general tool or the specialist?
So, the circuits were designed, the tests were run on real IBM quantum hardware, and the results were, well, let's just say they weren't even close.
The first jaw-dropping result was all about simplicity. The AI-evolved circuits had a staggering 93.8% depth reduction on average. Now, in quantum computing, depth is basically how many steps are in your program. A deeper circuit takes longer and has way more chances for noise to creep in and cause errors. So the AI solution was more than 10 times simpler than the human-designed one. And in the noisy quantum world, simpler isn't just better, it's everything. But of course, simplicity means nothing if you don't get the right answer. That's called fidelity. And this is where the AI just ran away with it. For one specific test, the evolved circuit hit almost 95% fidelity. It was right almost every time. And the standard textbook algorithm, it only managed 63%. That's barely better than just guessing.
The AI didn't just outperform the old method, it was in a completely different league.
Okay, I know what you're thinking. An amazing result, for sure. But science is about proof. Was this just a lucky shot? A one-off result on one specific problem? Or was this something more? Well, this table tells the whole incredible story. They ran the test for 8 different target states, and the result was the same every single time. Just look at 2 columns here. First, fidelity. The evolved circuits, in bold, are consistently up in the 90s, even hitting nearly 98%. The standard Grover algorithm? Stuck down in the 60s, barely working. Now look at depth. The evolved circuits have depths like 10, 11, 12. The standard ones, they're all over 170. This wasn't a fluke. This was a clear, repeatable, total domination. So what's the big picture here? What does all this mean for the future of quantum computing? Well, this isn't just about a slightly better algorithm. It's a completely new way of thinking. A whole new blueprint for how we should be programming these incredible machines. And Arons Obidiegwo, the study's author, he said it perfectly. He said we evolve many algorithms, each optimized for searching for one state. The philosophy is a total game changer. Stop trying to build one universal tool that does everything just okay. Instead, let's evolve an army of specialist tools, where each one does its one job perfectly. It's a shift from one-size-fits-all to completely custom-tailored. So let's just boil this all down. Why does this matter so much? 1, it means we can start getting real, useful results out of the noisy quantum computers we have right now. 2, it proves that AI can actually discover new, better scientific tools than we can. It's not just optimizing our ideas, it's having its own. And 3, it gives us a new philosophy: build bespoke, tailor the solution to the problem. That might just be the key that finally unlocks the door to true quantum power. Which brings us to one final huge question. We've just seen an AI design a better quantum computer program than humans could. If it can master a field this mind-bendingly complex, what's next? Designing new drugs? Discovering new physics? What other great challenges of science is AI about to solve for us? It's going to be an amazing future to watch unfold. Thanks for joining me on The Explainer.